Hi, I am back again from MySlate, and in this video we will move on. If you remember, we were discussing the applications of derivatives in the previous video, and we looked at the rate of change of quantities. So here we will move further and discuss another kind of applications of derivatives, which is how to find equations of tangents or normals on a curve. So let us start right away. So first we will look at the generic problem, right, and then we will look at a specific example. So I would request you to first focus on this left diagram that's shown here. So let's say that we have this curve of a given function y equals fx, and our task is to find the equation of the tangent to this curve at a given point A. And further we are required to find the equation of the normal to this curve at the same point A, and the definition of the normal is that it is perpendicular to the tangent on the curve. Now let's first talk about the tangent. Okay, now tangent is a straight line, as you know, and you all probably already know that to find out the equation of the straight line, all you need is to know its slope and one point on the line. So let's say we already know this point A, its coordinates are x0, y0, so that we know. So all that we require to know is the slope. So if you know the slope of this line, so let's say the slope of the line is f prime x, and how do you find the slope of the line? Suppose you have the mathematical expression of this curve y equals fx, you could find the dy by dx from that expression, and then you find the value of that dy by dx at the specific point A, whose coordinates you know, x0, y0. So therefore you could find the slope of the tangent on this curve at this point A. So that's the slope, f prime x here, right. So if you know the slope and a particular point, you could find the equation of the tangent. And how did we get this equation? Well, that's quite easy. You probably already know that the slope, which we express here as f prime x, which let's say we are able to find out somehow from the equation of the curve at that particular point, that for a straight line equals y minus y0, where y0 is the given point, that's the y coordinate of this point A here, and y we use to represent a generic the y coordinate of the generic point. So y minus y0 divided by x minus x0. Okay, so x0 y0 refers to the specific point that we know, and xy refers to any generic point on this line, which is a tangent. And from this we can get the equation in these terms: y equals y0 plus the slope of the tangent multiplied by x minus x0. And remember that the slope of the tangent is found out from the equation of the curve by calculating dy by dx and then plugging in these values of x0 and y0. And now let's look at the normal. Okay, so we already know that the normal is perpendicular to the tangent, and both the normal and the tangent, they intersect at the same point A on this curve. Now from the slope of the tangent, can we automatically find out the slope for the normal? That's given here as minus 1 by f prime x. So f prime x is the slope of the tangent. So how did we get minus 1 by f prime x as the slope of the normal? Well, probably you already know it, and in case you don't, it's quite easy. You know already that the slope of any line is nothing but the tangent, the value of the tan theta, tangent of the theta, where theta is the angle that the line makes from the positive x axis direction. That's shown here by theta. And so in our case, f prime x is nothing but the tan theta here. Now when we are looking at the normal line here, that would make a different angle, because that's theta plus 90 degrees, right? So the normal would make an angle of, let's say, theta plus 90 degrees, because that's perpendicular to the tangent, and therefore what would be the slope of the normal? Well, that would be tan of theta plus 90 degrees. And you already know probably that tan of theta plus pi by 2 equals minus cot of theta. We won't derive that here, but probably you know this already. And what's minus cot theta? Well, we know that cot theta is 1 by tan theta. So minus cot theta is minus 1 by tan theta. And that's how we get this slope of the normal. That's minus 1 by f prime theta, because f prime theta is nothing but the tan theta, the slope of the tangent. So slope of the normal would be minus 1 divided by the slope of the tangent. And that's what we plug in the equation of the straight line here to get the equation of the normal. Okay, so let's now look at this simple example here to understand how we do it. So let's say that we are giving this curve y equals fx, and the equation of the curve is y equals x cube minus 2x squared minus 1. And here I have drawn a rough sketch of the curve. It's not too accurate. But let us say that our job is to find the equation of the tangent and normal on this curve at a given point B right here, and the coordinates of the B are known, let's say. So, and they are 2 minus 1. Okay. So, x naught equals 2 and y naught equals minus 1. Well, the rest of the procedure is pretty mechanical, as we've already seen. Our first job, as I mentioned, is to find out the slope of the tangent, which is f prime x. So let's call that m here, and we are given the equation of the curve, and we know that the slope is dy by dx, which is f prime x, and let's calculate that. So what is the dy by dx of x cube minus 2x squared minus 1? Well, from our understanding of derivatives, we already know that it is 3 times x squared minus 2 multiplied by 2 multiplied by x minus 0. So we have this as a slope, 3x squared minus 4x, and we see that the slope varies at different points because it's a function of x. So and we are interested in finding the slope at this particular point B, where x equals 2 and y equals minus 1. So we plug in those values and we get the slope of the tangent to the curve at that point as 4. And we already know the coordinates of that point. So with those two pieces of information, the slope of the tangent at that point and the coordinates of that point, we get the equation of the tangent, which is a straight line. And likewise, the slope of the normal to the curve at that point, we already know normal is perpendicular to the tangent, so its slope would be minus 1 divided by the slope of the tangent, so which is minus 1 by 4. We plug that into the equation of the straight line, and we get the equation of the normal. So that seems pretty cool, and let's look at two simple examples further to appreciate this. So example 1 is about finding the equation of a tangent, and the curve is given to us. It has this expression, and every time it may not be possible to quickly draw the diagram of the figure of the equation of the curve. If you can do that, that's great, but every time you may not be able to do that quickly. So you should be able to follow logically the procedure that we just saw. So here our task is to find the equation of the tangent to this curve at a particular point where this curve cuts the x-axis. Okay, so here we need to do two things before we can find the slope of the tangent. First, we need to find this point, the coordinates of the point where this curve cuts x-axis, and then we also need to find the slope of the tangent to this curve on that point, which means the value of dy by dx at that particular point, and then we can find the equation of the tangent. So let's start. So we have this equation of the curve, and please note here, always keep in mind the points where this is not defined. So because this curve, we already know this function would not be continuous at those points. So the denominator vanishes at these 2 points, x equals 2 and 3. So we are talking about every point other than those 2 points. The points which are in the domain of that function, and we can see that because numerator and denominator both are polynomial functions, so except for x equals 2 and 3, this function is continuous everywhere else on the real line. Okay, so let's now find the coordinates of the point where this cuts x-axis. We know that y equals 0 everywhere on the x-axis. So we simply plug that in back into the equation of the curve, and we can easily see that x equals 7 at that point. So the coordinates of that point are 7, 0. And now the other piece of information we need is dy by dx, that is the slope of the tangent at that point. So we need to do a little bit of calculation there, a little bit of algebra. So dy by dx, we simply take the derivative of both the sides with respect to x, and we use our usual formula for the derivative of a rational function which has a numerator and denominator. So see here we have the denominator squared, and on the numerator we have the derivative of the numerator which is x minus 7, which is 1, and multiplied by the denominator minus the numerator multiplied by the derivative of the denominator. And denominator, because it is the product of two functions, we again apply the product rule of derivatives to find out the derivative of the denominator, and then we further simplify it. And here you might be wondering where this y came from. Well, this is just a simplification. You don't really have to go all this far, because all that we need to do is plug in these values of x and y, 7 and 0. We could have done that even at this stage and found out the slope, but we are just simplifying it further. What we have done here is we have divided both the numerator and denominator of this expression by x minus 2 multiplied by x minus 3. So that's how we got rid of the square here in the denominator, and in the numerator we got this 1 here, and then here we could get y, because we know that y equals x minus 7 divided by x minus 2 and x minus 3. So that's what we got, how we got y here, and that probably just simplifies the calculation. But as I said, you need not have gone this far. You could have plugged in the value of x equals 7 right here, and now that's what we do here. We plug in those values and we get the slope of the tangent at that point as 1 by 20. And the remaining task is pretty straightforward. We plug those two pieces of information, the coordinates of x naught and y naught, and the slope of the tangent at that point, in the straight line equation to get the slope, the equation of the tangent. Let's look at the final example. Here we need to find the equation of the normal to this curve, y equals x cube plus 2x plus 6, and we are also given that the normals, there could be more than one normal. That's possible, because we might have 2 points on the curve of the equation that we are probably looking at, which might be the case here. So here it's given that the normals are parallel to the this straight line, right? So it's possible that there might be more than one normals parallel to this straight line, or there may not be any normal, right? Because you may have some complicated shape of the curve. So we'll not draw the figure here, but we'll follow the similar procedures. So we already given that the slope of the normals are the same as the slope of this line, and that slope is minus 1 by 14. How did we get that? Well, you probably already know that in the equation of the straight line, the slope is nothing but the negative of the coefficient of the x variable divided by the coefficient of the y variable. And if you are still not convinced, all that you need to do is, in this equation, you take derivatives of both the sides and you try to calculate dy by dx, right? If you do that, you would get pretty quickly this slope of this line. So the normals have the same slope that's given to us, and and we know that the slope of the normal is minus 1 by slope of the tangent. So we will also derive the slope of the normal from this equation of the curve. So for that, first let us get the slope of the tangent at a generic point xy, and that's dy by dx. So we basically calculate dy by dx, the expression for dy by dx. So that's pretty straightforward again, and we know that the slope of the normal at a point xy would be minus 1 divided by the slope of the tangent. So we have got the mathematical expression for that, which is minus 1 by 3x squared plus 2, and we equate that to the slope of the normal that we know already. And by solving this equation, we get two possible values of x. So you see here that there are 2 points on this curve where we have normals with this particular slope 1 by 14. So x could be plus and minus 2, and corresponding to those two values of x, we substitute them back into the equation of this curve to get two possible values of y, which comes to 18 and minus 6. So therefore, we are talking of these 2 points on this curve, 2, 18 and minus 2, minus 6, where the normals on the curve have the same slope, which is minus 1 by 14. Okay, and now the remaining task is pretty straightforward, that at each of these points whose coordinates we know and the slope of the normal we know, we need to find the equation of the normal, and we, for each of those points, we plug those pieces of information in the straight line equation to get two equations for the normal, right? Please remember here that although these two normals have the same slope given here by minus 1 by 14, but the equations are not the same, because those two normals don't represent the same straight line. They are different straight lines, parallel lines because they have the same slope, but distinct lines, and they cut this curve at two different points, which are given by these two coordinates. Okay, so I hope you have understood this simple application of derivatives to find the equations of tangents and normals on a given curve at a given point, and I'll now see you in the next video. Okay, goodbye.